Number 1. F of x equals x squared from x equals 1 to x equals 5. The first graph here says use 4 equal rectangles whose height are the left endpoint of each rectangle to approximate the area, something we will call LRAM. So LRAM, again, stands for left rectangle approximation. So what does that mean exactly? Well, let's take a look at some rectangles that are sort of already begun to be hashed out here. I want to make sure you understand what that means, left rectangle. So on this partition from 4 to 5, the height of that rectangle is at the leftmost point. It's at the 4, so go up and there's the height. Again, left means the left of the partition or interval, 4 to 5, would be the height. The next rectangle for that would have its height at the left point 3, and then at the left point 2, and finally at the left point 1. And we would use these rectangles to approximate the definite integral, left rectangle approximation method, LRAM. The integral from 1 to 5 of x squared dx is going to be approximately LRAM, which equals, we're going to add up these rectangles. Now, let's take a step back here for a second. We're going from x equals 1 to x equals 5, and in the problem it wants 4 equal rectangles. It's obvious to us by looking at it that change in x will equal 1, but how do we figure that mathematically? Change in x is going to be the distance that we cover, in this case b minus a, or 5 minus 1, and then we're going to divide by how many ever rectangles we want. We wanted 4, but in general we might want n rectangles. So change in x is going to equal 5 minus 1 divided by the 4 rectangles that we want. 4 over 4 is equal to 1. So change in x is equal to 1. But when you fill this out in the notes, I would like you to pretend that you don't know what change in x is so that you can follow the format. So the first rectangle is going to be f of, and this is the key to the problem, to make sure you use the left points. So the first one is going to be f of the 1, the left endpoint, times the change in x. Now we'll go to the next rectangle, which will be f of the respective left, which is 2, times change in x, plus f of 3 times change in x, finally plus f of 4 times change in x. And we stop there because you should see that the f of 4 will give us the height of the last rectangle. Next, what we're going to do is come down, so change in x is constant, so I'll pull out the change in x, which leaves me with the f of 1 plus f of 2 plus f of 3 plus f of 4. It is at this point I will plug in what I know change in x to be, 1 for change in x. F of 1 would be the value of the function f at 1, which is 1 squared, plus f of 2, which will be 2 squared, 3 squared for f of 3, and 4 squared for f of 4. Now we'll just do that arithmetic, and that comes out to be 30 units. The next part wants us to estimate the same integral, but this time using a right rectangle approximation, or RRAM. That's where the height of each rectangle is the rightmost point of the partition. So if I draw these rectangles carefully, you see that the height occurs at the rightmost point for each of the rectangles. Height occurs at the right point, the right, and at the right. So we'll come over here and say the integral from 1 to 5 of x squared dx is approximately RAM, right rectangle approximation method, which equals f of the first f will now be f of 2 times the change in x, plus f of 3 times the change in x, plus f of 4 times change in x, and then the last time is f of 5 change in x. I will pull out the change in x, left with f of 2 plus f of 3 plus f of 4 plus f of 5. The change in x is still 1. And now we have new values here. 2 squared 4, 3 squared 9, 4 squared 16, and 5 squared 25. We do the arithmetic, add that up, and it comes out to be 54 units. Clearly, using the right endpoint for this particular graph will be a gross overestimate of the integral, whereas the left was a gross underestimate. That's because the curve here was increasing. Next graph wants us to use the midpoint of the partition to be where the height of the rectangle occurs, or MRAM, midpoint rectangle approximation method. So let's come over like we've done. We'll draw the rectangles going down. There's one. See how the height occurs at the middle point? There we go, right in the middle there. That's where the height occurs. In the middle where the height occurs, and the last one where the height occurs. So I think you get the idea here. Now we'll have the integral from 1 to 5 x squared dx is approximately MRAM, midpoint rectangle approximation method. So we're going to need f of, this is the key, what the f of is, f of 1.5, so we'll write that as 3/2 times change in x, plus f of 5/2 times change in x, plus f of 7/2 change in x, plus f of 9/2 change in x. Pull out the change in x, we're left with just the f of values as I'm writing them here. Alright, now I'm ready to plug in some actual numbers. 1, let's see, 3/2 squared is 9/4, 5/2 squared 25/4, 49/4, and 81/4. Not too bad, the arithmetic here, and that will add up to be 41 units. For the last graph, we're going to use trapezoids to approximate. So you won't actually find this word, I made it up, but it sort of follows the pattern. I'll use TR for trapezoid approximation method. TRAM, if you will, or perhaps TRAM, trapezoid approximation method. So let's show some of these trapezoids. I'm going to highlight our points on the graph with these dots. I'm going to connect the dots and draw the trapezoid. Do that with the next one. Draw the trapezoid, and yet the next one. Trapezoid, whoa, a little sloppy there, and trapezoid, drop that guy down. Boom. There we go. We've got our trapezoids. So the integral from 1 to 5 of x squared dx is approximately TRAM, trapezoid approximation method, which equals, so we notice here, hopefully we notice here, that the partitions, the change in x partitions, are all the same. See, each one of these is going to be 1 unit. That lets me use the version of the formula where I pull out change in x, and I pull out 1/2, so change in x over 2. And now the all-important f ofs. Can you see it? that the endpoints are singletons. This base and this base are singletons, and the ones on the inside will be shared, so they get doubled. So we have f of 1 plus 2 times f of 2 plus 2 times f of 3 plus 2 times f of 4, and finally the last base singleton f of 5. Changing x is a 1 over the 2, and now we have each of the f values. 1 plus 2 times 4 plus 2 times 9 plus 2 times 16 plus 25. Let's do the arithmetic. That's going to be 1/2 times 84. So that comes out to be 42 units. There are no more graphs on the page, but I would like you to go to the bottom and do one last thing. Can you guess what I'm going to ask you to do? Hopefully you're thinking, what is the actual answer of the integral 1 to 5 x squared dx? Press pause now, work it out, and then check your solution. This is going to equal, can't forget the fundamental theorem of calculus part 2. First we need an antiderivative, which is x cubed over 3. And we're going to evaluate that from 1 to 5. Plug in the 5. 5 cubed over 3. Now plug in the 1. 1 cubed over 3. So we have 125 over 3 minus 1 over 3 for a 124 over 3. And that's going to simplify 41 1/3. The real answer. I'm hoping at this point you're thinking to yourself, if I can do it, actually, why in the world would I use any one of the approximation methods? Or perhaps you're thinking, why do the RRAM, LRAM, MRAM, and the TRRAM? Well, the truth is, I'm not going to ask you to do all of them. I will ask you to do one of them, and I will be specific. Use the LRAM, I might say. Use a right Riemann sum, which would mean RRAM, or midpoint, or trapezoid. I would give you one to use, and you would use it. But the question still remains, if I can do it actually, why use approximation at all? And that will be addressed on the next page of the notes.